pulse lasers.
Pulse, yes.
Yeah. So pulse laser means a short pulse for a short moment,
Yeah.
then a pause, then the next pulse. And to make a repetition, different repetition rates. Continuous wave means you have constant output of laser energy. We don't use it for this type of welding because the process which results with a continuous wave laser must be automated, because you need to fade in and fade out. That means you need to control the energy on the welding line. And for a pulse laser, it's quite good for manual work, because you anytime can stop, can go back and go again. That's perfect for manual work. Okay, so we use a pulse laser. We use neodymium lasers from the type of the material and from the characteristic of the output, the emission, we use pulse one. Okay, and how these lasers look real, you have a laser rod. This is the laser material. You have by side a flash lamp, which gives the energy to the laser rod. So this is the pump source for the laser rod. This is installed in a reflective housing. We use a ceramic reflector so that all energy from the flash lamp comes to the laser rod and not in other areas. This is called cavity. So inside the cavity you have the laser rod and the flash lamp. And there's a filter glass between and a little bit more. All this need to be cooled. Use water cooling. Okay, so you have the cavity and you have these two mirrors. Full reflection and a little less reflection. So the laser beam comes out in the direction of the laser rod from this mirror. Here you have the laser beam if this is active. Okay, and in real it looks like this. This is the cavity. You see this are the contacts for the flash lamp, here and here. And here inside you have installed the laser rod inside. And you see here are some tubes, water tubes. This is to cool the cavity. You need to cool the flash lamp and you need to cool the laser rod. So that means inside the cavity there's all around water. Water, distilled water.
Yeah.
Okay, and this flash lamp, it's a krypton lamp, you need to ignite. And this we do with high voltage up to 40 kilowatt. This is the electronic, it's inside here, and that is why this cavity is isolated against the housing, because of this high voltage. And inside this there's a circuit to make high voltage, short pulses of high voltage to ignite the flash lamp. Usually you have only 1, 2 or 3 pulses of this ignition electronic to ignite the lamp, and then it works continuously and the ignition circuit is switched off. Okay, then you see, where's my cursor? So this is the cavity, and you see 2 mirrors. This is we call back mirror. This is the 100% mirror. This is another mirror. And the laser beam comes out in this direction. Yeah. Okay. Between you have this component, which is called shutter. This is a safety component. This is to interrupt the resonator inside if something happens. So usually this shutter is closed. This shutter is closed, and only if you trigger a pulse, then the shutter opens, and this resonator is, and then you have this resonator. The resonator is free. The laser beam path is not interrupted. Okay, so this is a safety element. the shutter. Anytime closed if something unusual happens. Okay, so this is the design of a quite old laser, more than 20 years ago. And we will see the real system. You see, it's more advanced what we use now, and to more high power, but basically it's the same. So if you look to the components we have inside the laser head where the laser beam is generated, you have the crystal or the laser rod, you have the flash lamp, you have a reflector. All this is inside the cavity. You have the back mirror, HR mirror, high reflecting mirror. You have the out coupling mirror, which is semi-transparent, and the laser beam comes out in this direction from the resonator. And you have the beam shutter between to be able to interrupt the laser beam path, which is this red one. Okay, the next one behind this mirror is the so-called telescope. It's a two-lens system where we can change the focal plane. And the focal plane depends from the distance of these two lenses. We have one output lens, which is fixed, and we have an input lens, which and we can control the position of this input lens by a small motor, by the controller. Okay, the next is a 45-degree mirror for deflecting the laser beam from horizontal down to the vertical. Then we have an objective, a very high quality objective, to focus the laser beam with this cone to the focal plane.
Yeah.
And since this is so expensive, we have a protection glass here to protect this objective against sparks or smoke which comes from the welding.
Yes.
Okay, so these are the common components of the laser, and we look through the microscope through the same objective to the welding area in this way. We have 45-degree necked microscope with oculars here, here is a mirror system, prisms inside. Then we have a laser safety filter to protect your eyes against the laser beam.
Okay.
It's a fixed one, you look through. Next is we call microscope shutter. This is also an element. It's before it was motorized. Now we have since a couple of years we have an LCD shutter here. This shutter anytime closed in the short moment of the pulse. So if the laser pulse is generated, the view is closed and it opens immediately if the pulse is over. This is to protect your eyes against the visible light from the welding light.
You don't need a protection, additional protection.
No, usually not if you look through the microscope.
Okay.
But you see later, since it's possible to do this welding and not look to the microscope but from the side, that's the reason why they in Europe ask for wearing protection goggles anytime, also if you look through the microscope. Usually it's not required because you're fully protected so long you look through the microscope.
Perfect.
Okay, yeah, these are the components of a neodymium laser, which is flash lamp pumped. Yeah, so the energy to pump the laser material comes from a flash lamp. It's a neodymium laser, flash lamp pumped. This is one type of lasers we use for this kind of applications you have. Second one is a so-called fiber laser. We call these types FSS lasers. which is totally different. It looks like this, the generator. It's a box, and the laser comes along this optical fiber, and this is the output. That means the laser is not generated in the laser head, it's generated in this small box, this one, and comes along this cable up to the laser head from the back. It means all these components, you don't need a flash lamp, you don't need a cavity, you don't need these mirrors, because the laser already comes out of the fiber, it's ready.
Okay.
So we don't generate the laser. And you don't need water cooling at this place. You don't need high voltage at this place. That means that this type of lasers don't require any service. You can imagine this is very sensitive. All this you will see later downstairs.
Yes.
And an FSS laser makes it quite more simple, all these machines for
It's
servicing.
diode lasers. Diodes.
Diodes, yeah,
Is the power is the source.
the
the
pump
laser.
source. The laser diodes are the pump source, and the optical material is a terbium fiber. So an optical fiber which is dotted with terbium.
Yeah.
Okay, this is totally different technology. We have
It's
this
simple.
simple.
Yeah.
Yes. Not really simple. Simple for the user.
Yeah.
Not simple from the
Yeah, no,
technology.
the technology is the process.
Yeah,
Yeah.
the process quite more.
Yeah.
Okay, more effective or more efficient.
Yeah.
So for flash lamp lasers, all the energy you put in from this lamp and the energy, the laser energy which comes out here, if you set the relation, then only 4% of the energy you put into this machine comes out. 4%. That means if you want to make a 100 watt laser, you need 4 kilowatt power consumption to make 100 watt laser power. And this is totally different to a FSS laser. So you can generate 150 watt with just 800 watt input. Okay, so it's really a quite good technology. I will show you later and explain more details. Okay, what's this? This is just to explain. Anytime it's required to bring your workpiece in the focal plane of the laser.
Yes.
And is how to do this. You do it by this motorized axis, and you have different types of machines. They must be very flexible to reach every region. If you have big molds, you don't need to repair the full mold. You have small parts where you have to repair, but you need to reach this and have to move very precise in this area. And that's the reason why we develop these machines.
Yes.
Okay. I think this I explain later. No, maybe. There's some things you need to know. This is the schematic of a pulse laser. Yeah. So you have a diagram where this is the power and this is the timeline. And as I told you, for pulse laser, you have only for a short moment a pulse. Okay. And the maximum power you reach in this pulse is called peak power. But this and the red area means the energy of the laser. So the portion of energy which comes in this moment from the laser to the workpiece, which is used to heat it up. Okay, and so this is called the peak power, but you have to make it different from peak power to average power. Average power means you divide these red areas so that you have a continuous line. So the average power is quite less because you have pulses, energy only in a short moment. Here you don't have energy. And the average power, that is what is given from your technical details. There's written it's a 100 watt machine, 200 watt machine, 300 watt machine, 600 watt machine. So this does not mean the peak power, this means the average power. Okay, next is to explain the fiber laser. I don't want to do this, but just in general, this is a pulse. Again, the same diagram. This is P over T, power over time, timeline, and this is pulse. And this pulse has two characteristics or two settings. One is the peak power. On a fiber laser, it's set by the diode current. On a flash lamp pump laser, it's set by the voltage. And you have the pulse duration, or pulse width, which you can adjust on the YAG laser from 1 millisecond to 20 milliseconds. Okay, so this is how to adjust the energy of a single pulse with these two parameters, and the distance, time distance between this, you can make smaller distance, bigger distance, means the repetition rate of these pulses, and you can adjust at the YAG laser up to 20 pulses per second, 20 Hertz, and on a fiber laser you can go to 100 Hertz. But I don't want to explain the fiber laser now. Maybe in the next step we should go downstairs